Hi everyone, it's Ms. Chun. For this video, I'd like to introduce to you a new topic. Well, it's kind of new. It's related to what we've been talking about before involving double replacement reactions, but now we're going to consider scenarios that involve something called single replacement reactions. So just as a reminder, the double replacement reactions involved aqueous ionic compounds, so ionic compounds that were dissolved in water, and therefore that resulted in their ion switching places. So the cations would seek out new combinations with new anions to form new products, and sometimes those products would result in a precipitate being formed. And other times we looked at examples where there was an acid reacting with the base, and that would result in a neutralization reaction forming water. Well, now we're gonna apply it in a slightly different way. And now we're going to look at something called a single replacement reaction. So I'd first like you to look at the scenarios presented in number 1. So if we take a close look at the reactions in number 1, we'll see that the first example, we have solid iron reacting with aqueous copper 2 nitrate to form solid copper, and then aqueous iron 2 nitrate. But then if we look at the second scenario, we have a solid copper reacting with aqueous iron 2 nitrate, and then there's no reaction. So like similar atoms, right? But why would the first scenario result in an actual reaction where new products are formed versus in the second scenario, these two reactants try to mix, but then nothing happens, no reaction happens? Well, I can answer that by showing you something called a reactivity series. So at the top of this list are metals that are considered most reactive, and then as you go down towards the bottom, the metals get less and less reactive. There's a non-metal in here, hydrogen, but don't forget hydrogen does like to form a +1 charge, so it's a non-metal that also likes to lose electrons. So what does it mean for a metal to be more reactive? Well, as we know, metals tend to like to lose electrons to become more stable. So those that are at the top of the list are better at losing electrons than those at the bottom of the list. So this is how it can get applied. In this example, we're looking at specifically two metals in these reactions, iron and copper, right? Fe and Cu. So if you look at the list, iron is listed, let's see, right about here, and then copper is listed way down here. So by comparing these two metals directly, we can see that iron is a fair amount more reactive than copper. So if we apply that here to number 1, let's write down what we just found out. Fe, iron, is more reactive than Cu, which is copper. So how does that apply to these scenarios? Well, in the first scenario, iron started off as a solid and was successfully able to replace copper in solution, right? Because essentially what happened is, since iron's more reactive, when it tried to react with copper 2 nitrate, it was able to kick out copper, and so copper became the new solid, and then iron went into solution with the nitrate ions. Okay, kind of scandalous. But if you look at the second scenario, when copper starts off as a solid and tries to replace the iron in solution, it's not successful because copper is less reactive than iron. So the iron's like, nope, sorry, you can't replace me. So copper cannot replace iron in this second example since copper is less reactive than iron. So hopefully that helps to clarify number 1. So for number 2, what does a reactivity series show you? Well, it just shows you the relative reactivity, in this case, of different metals, including hydrogen, which is the non-metal. Things towards the top of the list are going to be metals that are better at losing electrons than things towards the bottom of the list, okay? And that's how we can predict whether a single replacement reaction will actually take place, is we compare the relative reactivity of the metal atoms that are involved, okay? So for number 3, let's try to apply what we just learned about the reactivity series. So in scenario 1, we are trying to change my color here. In scenario 1, we're trying to see whether solid lithium and aqueous aluminum sulfate will react. So the first thing we have to check on the reactivity series is we have to compare the relative reactivity of our metal atoms, right? Lithium and aluminum. So on the list here, whoa, lithium's way at the top. Okay, so that's going to be kind of hard to beat. And then aluminum is sort of down here. So we just found out that lithium is more reactive than aluminum. So let's write that down before we forget. So we just found out that Li is more reactive than Al. So what that means is that the solid lithium will be able to successfully replace the aluminum ion in solution. So what that's going to look like is lithium will kick out aluminum. So therefore aluminum will become the new solid metal that's by itself. And also I should note, when a metal becomes a solid, or if it starts off as a solid, you can assume that its overall charge is 0. So any solid metal is going to have a neutral charge, okay? But when a metal becomes an ion and goes into solution, that's when you have to pay attention to what charge it likes to form. So when lithium goes into solution, you'll want to look at the periodic table and you'll see lithium is in the first column, so it's going to form a +1 charge. Sulfate is still our anion, right, floating around in solution. So look at your polyatomic chart, you'll see SO4 likes to carry a 2- charge. So when Li plus combines with SO4 2-, they're going to form Li2SO4, right? We need 2 lithiums to balance out this sulfate. And now they're going to be in solution together, so we'll call that aqueous. And so the final step is just to balance this equation. Let's see, I see 3 sulfates on the left side, so I'm going to need to write a big 3 in front here. And then that creates now 6 total lithiums, so I'm going to put a 6 in front of Li there. And then I have 2 aluminums on the left side, so I'm going to put a big 2 in front of Al there. And this would be my final balanced reaction. And this is how a single replacement reaction takes place, okay? So it's called single replacement because a metal atom is trying to kick out another metal ion that's a part of an aqueous ionic compound, okay? And so let's look at our second example here. It's between, let's see, solid silver is trying to react with aqueous potassium nitrate. So we're interested in comparing the relative reactivity of silver and potassium. So if we look at our reactivity chart, we can see that silver is way down here, and potassium is way at the very top here. So sorry silver, potassium's way more reactive. So let's write down what we just found out. So we found out that K is more reactive than Ag. So what that means is, as the solid silver trying to replace the potassium, that's not going to happen because potassium is more reactive than silver. So potassium's like, nope, sorry, I'm staying in solution. You can't replace me. So therefore, we're going to say that there's actually no reaction that happens for this second example for number 3. Silver and potassium nitrate will not be able to form any new substances. You can try to mix them, but nothing will happen. No reaction will happen. So there we go. So that's number 3. Hopefully numbers 1 through 3 gave you some examples for how to apply this new piece of your reference material. Don't worry, you don't have to memorize this. This will be on your a permanent fixture on your reference slides now, how to apply this reactivity chart. Okay, so there's one more layer to this. It's not done quite yet. The next thing I want you to show involving these single replacement reactions, we're going to take a slightly closer look at what's actually happening between these metals. And what's actually happening is there's a transfer of electrons. So the whole reason that the solid metal can go into solution and replace another metal is because electrons are being transferred. So in order to see exactly how the electrons are being transferred, I'm going to show you now how to write out something called half reactions. So in order to do that, it's always a good idea to start off with the balanced chemical equation. So here we have 6 Li solid plus, and then it was just a 1 there, so it'd be Al2SO4 3 aqueous, and that's gonna form 3 of the Li2SO4, that's aqueous, and 2 of the solid aluminums. Okay, so there's our balanced reaction from the previous example. The very first thing I'd encourage you to do would be to write out a complete ionic equation. So this is kind of something we covered way back when. We're going to do something slightly different though this time around with the complete ionic equation. I want you to keep the coefficients in the complete ionic equation. I know we didn't do that last semester, but this time around it's going to be important because we're going to have to keep track of the total amount of electrons that are being transferred. So as a reminder, anything that's aqueous is going to get split into its ions in the complete ionic equation. And then anything that's any other state of matter, solid, liquid, gas, you're just gonna rewrite those things as they are from the balanced chemical equation. So, for example, we start off with 6 of the solid lithiums. So I'm gonna just copy that down, 6 Li solid, okay? And then the next thing I have here is I have Al2SO4 and that's aqueous. So if it's aqueous, you're going to split it into its ions. So it's going to involve an Al3 plus cation, right? And that's going to be aqueous. And then it's going to involve also an SO4 2- anion. That's also aqueous. And then we're going to go to the first product here, which is aqueous lithium sulfate. So we're going to split lithium sulfate into its ions. So it's going to be Li plus and then SO4 2-, right? And those are both going to be aqueous. And then we have, remember, keep this coefficient here. Since it's a solid, we just have 2Al parentheses S. But here's something now that we have to do. We have to make sure that we're balancing this equation. So since we kept the 6 in front of the Li, put a 6 in front of the Li plus here. Okay, and since we kept the 2 in front of the Al, put a 2 in front of the Al there. And now that we have the complete ionic, I want us to now turn that into a net ionic equation by canceling out any spectator ions. So by definition, spectators are the ions that exist in both the reactants and the products on the left and the right side of the arrow. So the one spectator ion is the SO4 2-. Now, why didn't I cancel out the 6 Li solids with the 6 Li plus ions? Well, because technically, solid lithium is not the same thing as the lithium ion, which is in solution. So you now have to really pay attention to the charges. If it starts off not having a charge and then ends up having a charge, you can't cancel them out in the net ionic. Same for aluminum, right? It starts off having a charge here, it starts off in solution, and then it ends up as a solid. Those things are considered different. So you can't cancel anything else out. So let's just rewrite what we have left here. So we have 6 Li solid plus 2Al3 plus aqueous, and that's going to give us 6 Li plus aqueous plus 2Al solid. Okay, so essentially what this is showing us here are the changes that are happening between these two different metals. Okay, and this is going to be super important. So you're going to use the net ionic equation to help you write two half reactions. So let's start off first by looking at what happens to lithium, since lithium's listed first here. So we start off with 6 Li solid, and then if we look what happens to lithium, we're going to draw an arrow. On the right side of the arrow, it ends up being 6 Li plus, and that's the lithium ion in aqueous solution. So lithium essentially goes from being a solid to becoming an ion in solution. And in terms of balancing out the atoms, this is balanced, right? Because we have 6 lithiums here, 6 lithiums here. But what's not balanced is the charge. Because don't forget, a solid metal has a neutral charge. It has a 0 charge. But if we have 6 lithium plus atoms, if each ion has a +1 charge and we have 6 of them, we technically have a net charge of 6 plus on the right side. So if we want to balance out the charges, watch what I'm going to do. I'm going to show that there needs to be 6 electrons. Each electron has a -1 charge on the right side, because 6 negatives and 6 positives will cancel each other out to give us a total overall charge of 0, which matches a total overall charge of 0 on the left side. Okay, so what this is showing is that lithium went from being a neutrally charged solid to becoming a cation, a positively charged cation in solution. And to do that, lithium had to lose electrons. Okay, so because lithium lost electrons, we're going to say that lithium became oxidized. Okay, so the thing that lost electrons, the thing that became more positively charged, is the thing that became oxidized. Okay, so the reason we knew that lithium lost electrons is, see how we wrote the electrons on the right side of the arrow here? Okay, so if you compare before to after, right, lithium started off with a 0 neutral overall charge, and then it ended up with a +1 charge. So that's how we know that it had to lose electrons. So therefore it became oxidized. That's the word we're going to use. Okay, now let's take a look at what happened to, I'll use black, what happened to this aluminum ion here. So we started off with this 2Al3+, and that was in solution. And then it ended up becoming a solid, right? So aluminum ended up getting kicked out of solution and it became a solid. So we have 2 aluminum atoms on each side of the arrow, but if you look at the overall charge here, the left side of the arrow has a total of a 6+ charge, and the right side of the arrow has a total of a 0 charge, right? Because the solid aluminums have no charge. So to balance out the charge, let's add 6 electrons to the left side of the arrow, right? Because 6 negatives will cancel out 6 positives to give you an overall 0 charge, which matches the 0 charge on the right side of the arrow. So what we can say happened to aluminum was that aluminum ended up gaining electrons, right? Because we had to write the electrons on the left side of the arrow here. So since, right, essentially Al3+ gained electrons, right, then we would say that aluminum, we would say got reduced. Okay, so here's where things get kind of weird. Technically, in question B, I'm asking you to identify the oxidizing and reducing agents. So it's kind of opposite here. If lithium became oxidized, that means that it was doing the reducing. So the thing that gets oxidized, or the thing that became oxidized, that's the thing that we call the reducing agent. Okay? And then the thing that got reduced is the thing that was doing the oxidizing. So that's why aluminum is going to be called the oxidizing agent. Okay, so it's kind of confusing. Sorry about that. But you have to think about like what that element is doing to the other element. So by lithium losing electrons, it was reducing the aluminum, and that's why lithium is the reducing agent. And by aluminum gaining electrons, aluminum was doing the oxidizing. So aluminum is the oxidizing agent because aluminum got reduced. So yeah, there's that. I'll let you practice that a bit more in the homework. Sorry if it seems a little bit confusing at first. And then the final question, sorry, I didn't really label my work here, so let's just recap what we did so far. So we answered part A, we wrote out the half reactions, that's what was happening up here. So this right here is part A. Okay, those are the 2 half reactions. And then part B, we were able to use the half reactions to figure out which element was the reducing agent and which element was the oxidizing agent. And then for part C, excuse me, we need to figure out the total amount of electrons that are being transferred. So if you notice in the first half reaction, right, lithium is losing electrons, and in the second half reaction, the aluminum is gaining electrons. So what that means is that a total of 6 electrons had to get transferred between the lithium and the aluminum to make this reaction work. So we would say 6 electrons total are being transferred, okay? And I'm using the symbol E with the little negative charge to represent a single electron, okay? And so finally for number 5, sometimes we refer to these single replacement reactions as redox reactions. So if you split up the word redox into 2 separate words, you end up with, the first part of the word has RED in it. That's referring to something that's getting reduced or a process of reduction, right? So in this case, the Al3 plus, right, the aluminum ion in solution was gaining electrons. And so that was the process of aluminum getting reduced and then forming just a solid aluminum. And then the OX part is referring to a process of oxidation, which in this case involved lithium becoming oxidized, right, because it was losing electrons. And so that's why we use the term redox to describe a reaction where electrons are being transferred, and in this case it's between 2 different metals. Okay, so there's that. Hopefully you'll get a chance to practice this. Thank you for listening to my video. Sorry I got a bit long. Reach out if there are any questions, and good luck with the rest of your homework.